very much. So we can start again. Yesterday, before I lost my voice, I was explaining that you can look at the minimization of this problem. So first I rewrote on the board the energy we're looking at, the Gibbs measure with the parameters for temperature. And so yesterday I talked about the question of minimizing this simplified energy among probability measures, and there's a unique minimizer, which is the equilibrium measure. And then you can say, okay, well, but what's the connection with the original problem? So it is true that if you have minimizers, and this is something that needs to be proven, but you can prove without too much difficulty. If you take the empirical measure of the minimizers as n goes to infinity, it will converge to the equilibrium measure. So if you want, that's a sort of zero temperature situation. And zero temperature is beta equals infinity, because for us, beta is the inverse temperature, right? So what about the situation where you have temperature? Well, it turns out that, so this can be made into a theorem. And by the way, everything I'm going to discuss, you can find it in the book that I wrote, which is on the archive as under the title Lectures and Coulomb and Riesz gases. So if you want more details, more proofs and everything, it's in there. Okay, so with temperature, it turns out that it's a little bit more exact or more relevant to add an entropy term to this and define the same energy plus 1 over theta integral of mu log mu. Okay, so here you're adding some sort of entropy, and theta is this guy. Okay, so now when theta is very large, then this becomes a sort of small perturbation. You could neglect it if you want. And it is going to be the case that theta is very large. If, for instance, you decide to have beta fixed, then n1 minus s over d is going to always go to infinity, and theta is going to be very large. But you could decide that maybe you take theta to be 1 or to be something of fixed order, then it would correspond to a regime where beta is actually quite small, and so that would be a rather large temperature. And so you see that at large temperature, you really need to have a sort of entropic correction here. And in any case, even when theta is very large, this is a better description than this. And this thing, again, has a unique minimizer that I'll denote mu theta, and which we call the thermal equilibrium measure. So it includes thermal effect. And what you can check is that this guy, contrary to the equilibrium measure, is no longer compactly supported. It has full support, and it has tails. Okay, so while the equilibrium measure was doing something like this, or maybe something like that, in terms of the density profile, the thermal measure would instead do something like that. So it would have tails. Boom. Something like that, or something like this. So it's still a probability measure. And there is a length scale, obviously, related to the tail here. So for instance, here you can see there's a length scale. And this length scale is 1 over square root theta. So when theta gets very large, this becomes very small, and so the jump is really almost happening, but it's sort of being smoothed out by the thermal effect. So anyway, this measure is also nice, and we study it for its own sake, and we can show that as theta goes to infinity, of course, it approximates the equilibrium measure. You can even know how precisely it approximates it. So in fact, if you want to know what happens with temperature, you can phrase a little theorem, which in mathematical language would be called a large deviations principle. But if you don't want to know what that means, Yes? There's a question. Yes, thank you.
Could we work with potentials that go to infinity at some point to make the support happen?
So the V that's up there, you mean? So V has to go to infinity at infinity, but you want to make it like really like
At a point.
or outside of a set or something. You want to make a sharp,
Like a confining.
like a seriously completely confining. Yeah, you could do that. Yeah. So if you do that, then there would not be tails. So the tails here, you can check the tails are like e to the minus v. Okay, so if you make v infinity, you're just gonna cut off the tails. But that in principle is okay. Yeah. We decided to work in a setup where v is not taking infinity values, but it's not. It wouldn't be very different. Yeah. Okay, so the large deviation principle I wanted to mention was that if you take an event, which is the event that the empirical measure, so I'm going to state it in a kind of informal terms. Take the empirical measure, and you say that empirical measure looks like a given probability mu. So the proper way to do it is to say it falls in some ball centered at mu and of small radius. Then that thing is like e to the minus theta n e theta of mu minus e theta of mu theta. And so how to read this thing? So first of all, you see that this guy is the minimizer of e theta. Okay, so this is always non-negative. And if it's strictly positive, I mean, if it's bounded below by some positive number, this probability is going to be very, very small. So it's going to be exponentially small probability, except if mu basically is like mu theta. Okay, so it means that the events where mu is very different from mu theta are very rare events, and you can quantify how rare they are. Okay, so you can say that roughly this is telling you empirical measure is like mu theta. And so this is a sort of variation on the same theme. You see, without temperature, it's mu v. With temperature, it's this sort of corrected version of mu v. But if theta goes to infinity, you can replace one by the other. It's not very different. Whereas if theta is not going to infinity, then this is really the correct thing. Okay, so as long as theta is much larger than 1, mu, the empirical measure, is very similar to the equilibrium measure. And that equilibrium measure would be a good description of the system. However, this one is always a more precise description. It's interesting to keep it. Anyway, I don't want to talk about these measures for long, because what I'm going to do now is basically to use them to reduce to a system that is charge neutral. Okay, so what we're going to do is we're going to look at the energy and expand it near mu theta by writing that the empirical measure, well, is like mu theta, maybe, plus a sort of error, which is the difference, and expand. So, if you remember from yesterday, the energy you can rewrite in integrated form. Yeah?
Just wondering if the temperature is like theta with x to the power of 1 minus x you choose it so that the equilibrium measure is different from the one at is different from the one it's still mutual.
Okay, so the theta is also an inverse temperature, if you want, which corresponds to the precisely this length scale, right? So it is the thing that's going to characterize the variation of the thermal equilibrium measure. So if you want, it's the sort of effective temperature to see a macroscopic effect, a macroscopic thermal effect.
So this justifies the scaling as n to the...
Yeah, it justifies it because, right, another way that you can look at it is here. Then this is the same as theta over, so theta n, what did I say? Theta over n hn, I think. Yeah. And so that's a way of scaling things that's quite common, this sort of mean field scaling. So if you want to see basically at which regimes of temperature you see a thermal effect, it's this regime. It's when theta is of order 1. Now you can decide you work with theta much larger than 1, then you can neglect the thermal effects in this macroscopic setting. You could decide to work with theta much smaller than 1, in which case the thermal effects dominate. Right? So this is the sort of crossover regimes where the thermal effects are gonna have a sort of macroscopic signature here. But for me, the more interesting regime is not when theta is 1. It's more when beta is 1. That's what I will focus on later. It's more like the regime where beta is 1, and that's a regime where you will see thermal effects at the microscopic scale. But yeah, there's all these regimes you can study. So you can try to pick one, or you can try to study all of them at once. Okay, so what I'm going to do here is basically take back the description in integrated form. So it would be given something like this. I abbreviate, of course, this is g of x minus y. And then you do the same with v. Right, and then you try to expand everything. So this one has a 1/2. So when you expand, there's going to be terms that have just mu theta, mu theta, mu theta. So these are going to give you the leading order term, which is a fixed term. And then there is going to be basically this sort of fluctuations terms. So terms that involve mu n hat minus mu theta integrated against fixed stuff. And these are going to essentially vanish due to the fact that mu theta is chosen to minimize something. So you're sort of doing a sort of expansion around a minimum. So linear terms are going to disappear. And then you find yourself with quadratic terms. So at the end of the computation, which I don't want to do because it's not that interesting, you find yourself with a new quantity, and I'm going to define it like this, denote Fn. And so now it's going to be denoted like that. Fn of a configuration xn. So from now on, xn is a shortcut for configuration. x1, xn. So a given configuration and a given probability measures mu, you can define this. So the difference between the empirical measures and n times mu. So here I just multiply everything by n. And because I have empirical measures here, or I have Dirac's, let's say, I have to again remove the self-interactions because they would give infinite terms. So we remove the self-interactions by looking at the complement of the diagonal. And this is a definition. Okay, so this is just a definition for now. which I view as a sort of next order energy. Where now you have the interaction of a system which you can think of as a neutral system, where you have n positive singular charges and a negative charge. So this minus n mu, you can view it as a sort of neutralizing charge, has the same mass, and has the opposite sign, and that one is, let's say, diffuse, right? So think of mu as something nice. Okay, so this is the support of mu, or maybe it has finite support, maybe not, maybe it's the equilibrium measure. Okay, so you can define this for any mu. That's a probability measure. And very quickly, I'm going to assume that mu has a density and that it's bounded, right? It has a bounded density. So that is satisfied by all these examples here. Equilibrium measures, thermal equilibrium measures. And so the relevance of this is that you can show after this little computation that the Gibbs measure can be rewritten exactly, so without any error, as exponential minus beta n minus s over d times this energy for the thermal measure here. Like that, and then you need a normalization factor. Okay, so this, and the normalization factor, sort of new partition function. We're going to denote it Kn, so it depends also on beta, and it's going to be a function of mu theta. Okay, so we can show this. So what we have done here is just pure algebra. Basically just expand around the leading order. This makes sort of additive sums of terms, some that are constant and some that are dependent on the configuration. Take out everything that's constant and move it outside and cancel it out with the partition function. So all the terms that are constant, we just put them in the normalization. And we keep what's configuration dependent, and this is just that. And here, the measure, the reference measure has changed. Instead of being dx1, dxn, it's become the measure mu theta. Okay, so now, based on that, yeah?
Is this, what is this, the probability for? Is it for the system or just for the fluctuation?
No, it's still the same probability. It's the same probability as above. It hasn't changed. The left-hand side is the same. The probability on the system, it's the Gibbs measure. So I'm just rewriting the Gibbs measure in a different way.
But I thought that F came from sort of a second order expansion. Where's the constant term?
So the constant terms, they cancel with the denominator. Right? You just take them outside. You have exponential of some constants, and in the bottom you have exponential of some constants. You decide to just cancel them out, and so you have to change the normalization. So this term has changed. So it's an equality. It's really an identity. So now, from now on, what you can do is you can just forget about how you obtain that, and let's just study. So I don't remember how I denote this even. Q. Maybe call it Q. So we can just do that for any reference measure. divided by, okay, so for any mu that you give yourself some reference measure with a nice, say, bounded density, and you decide to look at a system which is a Coulomb or Riesz system, but with this built-in neutralization. That's what you're doing. Okay, so instead of saying I look at endpoints, they repel each other, and there's a confinement, you say, okay, well, the confinement is just going to make it so that the points have to follow a certain density. That density now, I can view it as a neutralizing background charge. And so I can just look at my system as a neutral system with interactions between the points, and between the points at the background, and of course within the background itself. So all of these interactions are counted here in this double integral, right? The points interact with the points interact with the background interacts with itself. And you forget the confinement. You don't have to think about confinement anymore. The only effect of it was that it selected for you the reference mu. Yes?
So is K strictly less than Z, the original quantity?
Yeah. So in fact, what happens is that Z, the original one, if you take the log of Z, its really leading order is given by so something like beta n 2 minus s over d e theta of mu theta. And in fact, the K comes at next order. So this thing is dominant, and this thing is much smaller. So somehow you've taken out the dominant parts, and you're now being able to look at corrections to that by having divided by these very large leading order terms. Okay, so the part that's in mu theta, of course, that was leading, because that's the effective behavior. Okay, so you're looking at the next order, which is why I call it a next order energy. So this one is going to be much smaller. This one is much smaller than the original one. It's a correction to it, if you want. Okay, so this is not very far from what physicists call a gelium. So a gelium would be the situation where I would have a configuration of discrete charges and a uniform negative background charge, like -1. So a gelium, I think if you want to be correct, it corresponds to the case where you're already in infinite volume. You have these discrete charges, and you have the -1, which is like a sea of negative charge, and that keeps all that together. And so this is a bit of the same situation, except the background charge, you don't have to have it uniform, and the system is still finite. Is it clear? Yeah.
So we typically build a perturbation theory, but can we expect that this series will be converged?
The series?
You can expand in next orders some difference.
No. I'm going to stop here. I don't expand further. Okay? All right, so the point of this is that we want to deal with this long-range nature of the interaction that was alluded to yesterday. And you know that if you have a particle, right, and if you think of the Riesz potential that it generates, or the Coulomb potential it generates, this thing doesn't decay very fast. It's behaving like G, right? So 1 over x to the s, for instance. And that doesn't have very fast decay. On the other hand, if you think of a dipole, so if you had a plus and a minus particle, and you look at the potential generated by that, at infinity, it decays 1 order faster. Right? So instead of 1 over x to the s, it's like 1 over x to the xs plus 1. And this thing, potential is going to decay an order faster. And so now that you have the neutralizing background with you, well, effectively, it's as if you're looking at dipoles, right? Maybe, hopefully, like each plus comes with its little bit of neutralizing area. And so from far apart, you get a gain of an order of decay. And so that's part of the idea of the hope of what you can do after you've looked at it in this way. Questions? Okay, so from now on, I'm going to focus on this. And I'm going to try to explain what we call the electric formulation, which is that we're really going to start taking advantage of the Coulomb nature of the interaction. Coulomb or Riesz, but the precise nature of the interaction. So in some sense, everything I've discussed so far, you can do it for any G. You don't have to be Riesz or so for any repulsive kernel, the equilibrium measure makes sense, the thermal equilibrium measure makes sense, even the splitting makes sense. And by the way, I mentioned something yesterday. These types of things can be interesting also for G that are not singular, that are, let's say, with S negative. So when S is negative, not singular anymore, and bigger than -2. In statistics, it corresponds to things that are called MMD metrics, which is maximal mean discrepancy. So they are used, if you want, as a way to quantize a measure, right? You give yourself a given measure, it corresponds to some like distribution for your data or something, and you want to find Dirac's or empirical measures that best approximate it. So that's a quantization problem, and so that's one way of measuring how well you approximate your measure. Okay, so there's some connections also in statistics and stuff like that. Okay. So now, the electric formulation is going to allow us to rewrite yet again this energy in a different form. And for now, I'm going to assume that I'm in the Coulomb case, and I explained a little bit afterwards how to generalize to non-Coulomb Riesz interactions. So what we're going to do is we're going to define a potential. Now it's really an electric potential. We're really doing electrostatics when we're in the Coulomb case. So Hn is going to be a potential that depends on this whole configuration, Xn, and of course it's also going to depend on this background mu. And I'm going to define it as a convolution of G with the, so basically it's the empirical measure minus the reference measure, but here I normalize like this. Multiply everything by n, why not? Okay, so you see what convolution is, right? So you're really looking at the potential. If you prefer, it's integral of G, x minus y. Okay, so we have our neutral system, and we define the electric potential. And now, because G is the fundamental solution to the Laplacian, or if you're a physicist, because of Poisson's equation, you must solve, this thing solves minus Laplacian H, so I'm going to drop all the mu's, and this thing is equal to the sum of Dirac's minus n mu, and I have to put a constant in front, which was my dimension-dependent constant, okay? So I have this very nice equation, and this thing is solved in all of RD. Okay, so in fact, but you can also see how Hn is decaying at infinity, because this thing is neutral, so Hn is going to decay like 1 over x to the s plus 1, as we discussed. So there is a bit of a, you know, undetermination from this equation because you lose the sort of boundary condition at infinity. But if you define it like this, you have everything. Yeah, so here we have used Coulomb. And so now we're going to rewrite this guy. Oh, so maybe I do it below. So this guy, you see, there is a convolution happening here, right? I have a g of x minus y. I can see it as integrated against that. So I can recognize, if I do one integration, this thing, integrate it against that, integrate in y, I recognize what I define as hn. So remember, hn depends, it's a function, depends on x, and it depends on the configuration implicitly. So each configuration generates the field on the whole space, depends on x. Okay, so if I rewrite it like that, I'm going to write 1/2 integral. So now I do one integral has been done. So I find myself with hn. And I have another integration to perform. And it's just this one now, single integral. And now I observe that this guy is just basically the Laplacian of the electric field Hn. Right, so this is minus Laplacian Hn, where up to this 1/CD. Okay, so I rewrite this. And now, well, I want to use Green's theorem to integrate by parts this thing. Check that the Hn tends to 0 at infinity fast enough so we can do the integration by part. And find yourself with this. Okay, so we start from this. And we find this thing. So this is saying that the interaction energy is the integral of the square of what's the electric field. In fact, the gradient of the potential is the field. So it's the square of the electric field integrated about the whole space. And that gives you a different point of view on things. In particular, instead of thinking in terms of pair interactions, you know, like the points here interact with the point there, instead of having a double integral, suddenly you have only a single integral. And so if you think of your system as maybe chopped into pieces, maybe small pieces, boxes. In the first way of looking at it, you have, you know, if I look at this box, well, it interacts with that box. I have to look at all the pair, the interactions between points there, background here, background there. Once I translate it into this form, I just add the contribution to this cube and contribution to that cube, contribution of all the cubes. So it becomes a sort of extensive in space. In principle, easier to manage. And this is part of the thing that's going to allow us to, you know, say, do as if the energy became sort of additive over boxes. So in some sense now what you can think of is, well, you have an electrostatic system in each box, formed of points plus background. This thing has its own energy. And maybe if you're lucky, you can just add together these energies without looking too much at the cross interactions between distant boxes. And why does that have a chance of being correct? Because, well, because distant boxes, if the boxes are neutral enough, you know, like if the number of points in the box matches well the background charge in the box, then the field that they generate far away is small. That's this decay of the dipole potential. So if things neutralize quite well, what you should call it is they screen themselves, right? So these charges become screened by the background, and from far apart, they become like almost nothing, and so the energy has some chance of being essentially additive over these boxes. What we'll have to do, and we will do that today a bit later, is we're going to have to define what it means to count the energy of a system in a box, isolated from the rest. This is not yet very clear. Yeah? Okay, so now I've cheated in this relation that I derived here, so maybe someone can point out how I cheated you all. Yes? The diagonal, yes. So this is all wrong because of the diagonal. So here you have to pay attention to the self-interactions. If you don't pay attention like I did here, you find yourself integrating something. This Hn has the same singularity as the G itself, right? It has a Dirac in the right-hand side, so Hn near a point behaves like G of x minus xi near xi. Okay, now you can check this. If you try to integrate gradient of G squared, so near 0, of course. So it's the integral of 1 over x s plus 1 squared dx. And in all the cases we're looking at, 2s plus 1 is strictly bigger than the dimension. So this is always divergent. So except for the very regular cases. So typically this is always infinity. Okay, so by sort of putting back the self-interactions, you obtain an infinite result, which makes sense. But the idea is that it's okay. There's a way to go around it, which can call some kind of renormalization, if you want. We're gonna remove these infinities. To deal with that, and it's gonna be okay. It's gonna give a meaning to all that. So let's say a word about how to do that. So the way that we found convenient to do is to replace those charges by smeared charges. So the prime are the Diracs, right? The Diracs have infinite self-interaction. And for each Dirac, you can say, okay, let me look at instead. So replace delta xi by some new measure, which I'm going to call delta xi eta I, which is a uniform measure on the sphere of center xi and radius eta I, and of course uniform normalized to be of mass 1. Okay, so it's a thing that has the same mass, except the charge now is distributed on a sphere. You could do a ball, it would be fine. It's just convenient to use the sphere. You can use any radial rearrangement if you want. Okay, so do that. Question? No. And suddenly, this guy has a self-interaction which is no longer infinite. You can compute it. So if you compute that in the Coulomb case, it's exact. That's why the sphere is convenient. You get exactly g of eta I. So I'm here abusing notation a little bit. So g was a function that was defined on Rd. I make it also a function on R by saying, okay, g of a number is just the same formula, 1 over x to the s. So this is going to be 1 over eta I to the s, or log eta I. So the self-interaction is finite. Of course, it becomes very large when the radius becomes very small. So the idea is that we're going to try to put back. So first of all, you can show that the energy that you were looking at is the same as if you were taking the thing with the smeared charges. Yeah. So if you allow me, I'm going to do this to shorten my notation. So here I have the same interaction, except I have the smeared charges everywhere. And I don't remove the diagonal, so I have to remove the diagonal separately. And the diagonal gives me these self-interactions. So these are the self-interactions, and maybe there is a CD or something I should check. Pum, 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 pum. Okay, there's just a 1/2. Okay, so replace by smeared charges, put back the diagonal, and subtract it back. Okay, so you put it back, and then you subtract it. Now what you can check is if you take that, and if you take the eta I to all go to 0, you recover your original interaction energy. Well, because when it comes to the interaction between different points, well, when you let the radii go to 0, you refine the original interaction. So that's encouraging. So we could work with that, but there's something even better you can do. I need to send that up there.
So Sylvia, what is the self-interaction?
I think because there's a half in front of everything here. No? Okay, so we lost it for. Because there's a 1/2 here, that's all. So the 1/2 gets copied. Okay, so you can do that, but you can do even better because we don't like this limit. It's not very quantitative. You can use something which in physics is called Newton's theorem. So Newton's theorem tells you that the potential, I'm going to do it like that, generated by delta xi and delta xi eta I coincide outside bxi eta I. So in fact, Newton's theorem tells you the potential generated by a point charge and the potential generated by any spherically symmetric distribution centered at the same point, they coincide outside of the support of the, initially it was for planets, right? So the potential generated by a planet is the same as potential generated by a point charge at the center. So here that's true. And so in particular, if you have your points, and if you replace all the charges by these smeared charges, as long as the balls don't intersect, the interactions between the different charges is unchanged. So interaction between these two spheres is the same as interactions between these 2 points. because the potentials are the same. So the interactions are also the same. Okay, so interactions are the same. As long as EXI, eta I don't intersect. All right, and so once you've noticed that, you're like, oh, but then now I'm going to have an equality. I'm not going to have a limit anymore. I'm going to have that it's really equal. I just replace my charges by my smeared charges. I add and subtract the self-interaction. And there's only one thing that's going to change is the interaction with the background. Because you know, if you have a point interacting with the background, and if you have a smeared charge interacting with the background, that changes. But that changes by something explicit that you can exactly compute. So what we're going to do is we're going to define eta I to be what we call Ri, which is simply, let's say, 1/4 for safety, the minimal distance from xi to all other points. Right, so for each point, every time you have a configuration, you can look at the minimal distance for the point I to the other points, and you can take 1/4 of that. And those things are going to be disjoint, right? So the B, Xi's, Ri's are disjoint, with even some like buffer zone. And this is why it's advantageous to consider radii here, eta I, that may be point dependent. Because if you decide to fix yourself one eta for everyone, this sort of one size fits all is not going to work, because the configuration could have, like, you know, sometimes points that are very close. But if you do that, it's fine. And so then you can find an exact formula. So I'm going to summarize, not give you all steps. So the exact formula is going to replace Fn xn mu by something explicit. I'm going to denote like that, and I'll give you a definition in 1 second. So this sort of total interaction, where now we do this electric reformulation, minus all the self-interactions that get subtracted, plus some other explicit terms that I don't want to state because they're not that interesting, and they correspond to this change of interaction with the background. But it's all very explicit. And what is this? This is the potential generated by, obviously, by the smeared charges, right? So it's the same as before, but now you have smeared your charges at these radii, and subtract and mu. Okay? So if you want, instead of having these infinite self-interactions, you sort of smear a little bit. You get things that may become very large, but you subtract off the equivalent of the contribution to the self-interaction here. So modulo this, you've recovered the rewriting of that in terms of a single integral with the smeared charges. And from now on, since this is a class, we can do whatever we want. I'm going to just completely neglect this renormalization aspect. Okay, and I'm going to do as if, basically, I'm going to just write this. Right? As if I could give meaning to my first formula. But every time you see this, you should think, oh, this is to be meant in a sort of renormalized or truncated way. Because this is just something that's going to be carried over, but without really bothering us in the analysis. Any questions on this? Yeah.
I didn't understand why it was important to have different radius for different points.
It's just so that the balls are disjoint. Because you see that this theorem tells you they coincide outside, but if you had overlapping balls, right? If you have overlapping balls, you modify the interaction.
Why don't you just take the minimum?
The minimum what? But that's essentially what we're doing, no? We take the, you want to take the minimum over. Yeah, that's a good question, but if you take the minimum, it may happen that you're gonna basically be constrained by the smallest pair, right? There's gonna be one pair that's like really, really close, and it's going to make it so that this thing is gonna be all the time truncated at very small things. So this is gonna be very, very large, and this thing is gonna also be very, very large. And in the analysis, it's quite delicate if both terms become very large, although they cancel each other out. Not very good for us for the analysis. It's much better for us to do it like that, because what we can prove is that each of them is actually reasonably well controlled. So when you really take the minimal distance, you can bound this guy by the total value up to a constant, a multiplicative constant, and this guy also you can control it. So you don't really have a plus infinity, minus infinity situation. You have a situation where both are of reasonable size, and that's extremely convenient for the analysis. For things that I'm not going to show you that are going to be under the rug today, but there's definitely an advantage in not considering the worst case. In fact, the scale that you would want, that would be natural, it's not the worst case, it's the typical scale, which is the n minus 1 over d, right? That's the length scale of interparticle distance. But if you take that one, you have the problem of overlap. So now we have other techniques that allow us to sometimes do that, but this one is particularly convenient, I would say. Yeah?
This means that somehow, for good energies, you can tell that the points are sufficiently spread out. You managed to do that.
Yeah, so we managed to show, I mean, it's a consequence, in fact, of this representation that if the energy is controlled, then this guy cannot get too large. And that controls the minimal distances, right? So points that, if you have a pair of points that becomes very close, it's natural that the energy should blow up because the energy contains the pair interactions, right? But here you can quantify by saying you really control this guy by a constant times the energy. Right? So if you have a control on this, you have a control on that. It's very convenient. And this controls, you know, some form of small scale behavior. Not everything. So actually that's a good transition because one of the ideas is, now that we've rewritten the energy in that form, we're going to see that controlling the energy controls a lot of the behavior of the system. So I'm going to do this cheating thing that I announced now. I'm going to, from now on, do as if this was equal to this. And I told you that now this is convenient because this is extensive in space. And one of the things you can do, for instance, you can localize. You can define, given some region, omega, you can look at how much energy is in omega. All right, so this will be just all right. So I decide to look at this omega here. And I can talk about that omega energy. This is positive. It's a nice quantity. And what I'm going to show you is that this controls, for instance, what's called the discrepancy in the set omega. The discrepancy is the difference between the number of points and the background charge. All right, so we can denote it like this. D of omega would be the integral over omega of that. So you see that this is counting number of points, right? So it's number of points in omega minus. So this is kind of the expected number of points in omega. Right? This is how many you should have if everything was perfectly neutral. And this is the true number of points. And we can estimate the discrepancy by, well, we can define the discrepancy in this way. And so now the goal is going to be to see how, when you take omegas that can be possibly very small, so down to microscopic scale, can you have really big charge fluctuations or not? So if you can show that this d is quite small, it means you don't have large charge fluctuations. In particular, that's automatically going to control for you the number of points that fall in small boxes. Okay, so for instance, if you take a test function, smooth, and you want to understand what's the size of that, you test phi against this distribution. Now I can use the Coulomb nature of the interaction to say, well, this is the same as phi times the Laplacian of my electric field. So there's a 1 over CD or something, maybe a minus. All right, so then I can use Green's theorem again to write it as this. So let's say it's a compactly supported test function. And now I can just use Cauchy-Schwarz, right? So Cauchy-Schwarz is going to bound this by the L2 norm. And this guy. And maybe this is going to be in omega. Let's say this is supported in omega. So I have this in omega. Omega. And so now this thing is basically my energy. Right? So this I bound by square root of my f omega. Okay, so if I control the energy, that gives me natural controls on quantities like that. Or if you want, you can call that the fluctuation. So this is the first rough bound. We'll see tomorrow, not tomorrow, Friday, that in certain cases, when phi is smooth, you expect much better behavior even than that. This is a rough bound. We can get even a central limit theorem, like in some cases, limiting behavior for that random quantity. But okay, this is already interesting. And you can get with that some estimates on discrepancies by taking good, well-chosen phis. I'm not going to describe it all, but yeah.
Was there a smaller equal in the last steps? The definition of the next?
Here?
The next one.
Yeah.
Yeah, isn't that definition of what we call the
Yeah, this is an equal. Yeah. You want to say this is equal?
Yeah, yeah.
Yeah, this is equal. I mean, modulo all my cheating, but yes.
Sorry.
Yeah.
Question before you erase for the last formula, is this the sum of theta minus w or just w?
Oh yeah, there's an n. Thank you. Yeah. In this scaling, there is an n. Thank you. Okay, so if you want to get information on the discrepancy here, okay, so what can I do about the discrepancy? If I have a ball or some domain, let's say a ball, would be easier with the ball. And I would like to count how many points fall in that ball and what's the discrepancy with the measure. Or basically what you want to do is you have the indicator of the ball, right? indicator of the ball is like this. And you want to bound it above and below by some smooth profiles. All right, so you're going to use one like this and one like that. One phi like this, one phi like that. Apply this estimate and say that the number of points that fall in there is actually bounded above and below by the integral phi. Now mu you control well, it's bounded, it's an L infinity. So if you can make this sort of transition layer relatively small with respect to the size of the ball, so imagine this ball is relatively big and you have a sort of transition that's quite small compared to it. The error you make in the annulus is quite small. And you can get really some information from that. So I'm not going to write details, but maybe a statement for you. Discrepancies. I had it somewhere. Well. Yes. So in a ball of size R, there's something like that. You don't need to write this. This is just to give an idea that you can control the discrepancy to the squared by the energy in a double size ball. And in terms of R and S. Okay. So I hope I've convinced you that having good controls on the energy, on this energy, gives us interesting controls. And what we would want to have is localized controls. So if we start to take omegas that are smaller and smaller windows, can we still keep good controls? And this is going to be called a local law. So this is the thing we want to prove now. And this thing is going to come with, together, in fact, with two other notions. So it's going to be a local law. There's going to be a theorem. So in the Coulomb case, it's from a paper of Armstrong and myself in this generality, and a previous paper by Thomas Leblay in 2D. And now we're extending for Riesz. In a paper with Luc Pellin. And the sub-Coulomb Riesz, that's work in progress, but I think it's going to happen too. And the way to phrase it is, we're going to take a look at the exponential moments of okay, I should have defined something else before. Over 2. So hang in for a second for this definition. This thing is going to be bounded by, so here a cube of size R. It's going to be bounded by a constant times beta times the volume of the cube. And that's the theorem. And so what is my F here? Here it's more convenient to actually zoom the system. So sorry for the change of notation, but we had the following situation. We had a mu, maybe compactly supported, maybe not, was a probability. We had points. Typical length scale here is n minus 1 over d. So we're going to just zoom everything. Multiply everything by n 1 over d. So you find yourself with a box that has size n 1 over d. The points now are at distances more like 1. And the points are now going to be called xn prime. So there are n over d times xn. And the background is going to be called mu prime. So it's mu of xn minus 1 over d. And so the result of that is that mu prime is no longer a probability measure, but it has mass mn. Yeah, so integral of mu prime is equal to n. So it's still neutralizing. And the h prime is the thing that you obtain when you convolve xi prime. And now mu prime, you don't need to put an n in front anymore. And the f of xn prime mu prime is just this. So it's just the same story, but blown up, and you'll see that it's actually convenient to blow up. So in omega, you can do that. So, yeah. All right, so we look at the blown up thing. Xn prime is blown up. Mu prime is the blown up background, and here we restrict to qr, some cube of size r. Doesn't need to be centered in a specific place. No? So there is one restriction, though, I should say, maybe, is that if you have your background measure mu, which is like this, it's compact support, these things are only going to be true in the bulk. So you're looking at a cube that has to be inside. It cannot be getting too close to the boundary, or it cannot be here. There's like a sort of layer here, which is quite small, but the cube has to live outside of that boundary layer for this thing to be true. All right, so if you look at the largest possible scale, so here R, at most, the largest possible scale, it's when it's n 1 over d. It's on this picture. No? On this picture, right, this is the largest scale. I could come here with a box whose size is comparable to my largest scale. And I could come with a box whose size is smaller. At some point, I have to stop. So it has to be bounded below by some positive constant, otherwise the result will be wrong. So basically, the box has to be big enough that it has some points in it, some fairly large quantity of points. So there exists some constant C such that if you go above this size C, the local law holds. And of course, this C is relatively large, so you should imagine, right, this corresponds to a large microscopic box. Yeah? So if in the original scale, it would be n minus 1 over d times some large constant, so that you start to see some points. Start to see a consequential number of points in there. This is true for all of those. And if I want to be honest, there's something about temperature. So this constant here doesn't depend on temperature, or doesn't depend on beta. Here there is beta. And here this C depends on beta in a way that's degenerating when beta goes to 0. So when beta goes to 0, temperature is becoming very large. And then the sort of micro scale, or let's say the minimal scale above which you see this kind of good local laws, is getting large. And what's happening is that at very small scale, you expect that the system is more Poissonian, and the order starts to kick in when you reach a certain large enough scale. And that effect you see really when temperature gets very large, when beta gets very small. So this is a manifestation of some kind of good order of these systems, right? I told you that the point processes that come with them are expected to be much more rigid than Poisson point processes to have these properties of hyper-uniformity, for instance. So number of points in a box is not going to deviate too much. And this already gives us, we already get some controls from this, because if you remember, if you control that, you control these types of discrepancies. And this is a bound in what we call in exponential moments, right? So if this thing would become very large by a sort of Markov's inequality, it would have very small probability. You can estimate. Yes?
So here the mu prime there is arbitrary.
So you give yourself some mu at the beginning, yeah, that's your background charge. You zoom it, it's called mu prime.
It is unrelated to the point distribution.
Yeah, if you want, it's unrelated. I mean, it's given to you a priori, and this is the distribution. This is the distribution that the points are trying to emulate. Right? They're trying to look like it in some sense, because that's their negative background charge. And so for the energy to be small, they'd better look like that. You can think of it this way. So it's the thing that you pick. So it could be the equilibrium measure or the thermal equilibrium measure, but it can be any distribution that's relatively nice. Right? So you say you give yourself some distribution, and you look at this as a measure of a distance between your quantized empirical measure and your reference measure. That's another way of looking at it. Right? So it's like a Coulomb distance. Yeah.
It's not necessarily a question. I think it's to confirm my question regarding this question. Anyway, since we're blowing up, you will see a bad measure at the limit for this mu.
Yeah.
Mu prime.
Yeah. Right. So once you blow up, if you were to look at the local limit, like if you were to center near a point, this background measure would just become uniform locally. Right? So it has very slow variation now. Yeah. So just think of it as uniform. If you don't worry about general case, you can just think of this as a uniform measure with support in a very big set. And that's already good enough. Just think of -1. So this thing I claim is sharp. You cannot do better than that. You can also check that if you're at the largest scale, then QR would be the whole, if you take just the whole space. Here you're going to get the size of the largest thing. This would be volume n, right? Because you have a box of size n to the 1 over d. So a priori, you have volume n. And what's good about this statement is that when you look in a much smaller region, you gain something that's the volume of the region, right? It's no longer like n, it can be much smaller. So these local laws is point 1. And I said it's going to come hand in hand with 2 other ideas. We're actually going to prove them together. Okay, so this one, put it down. So number 1 is local laws. Number 2 is almost additivity of the free energy. And the third thing is screening procedure. So the screening procedure, which I'll talk about, is something that allows you to show this, the almost additivity of the free energy. And that's the thing that allows you to show at the same time the local law. So what is the free energy? I remind you, it's log K. All right, so I'm going to try to say a few words about this. So I mentioned before that I want to start defining what it means to be a system in a box like this, a charge system with points and a background, and look at the energy of that system. And if I can do that, I can try to show that the free energy, the log of the partition function, over this union of cubes is actually almost the sum of the free energies over cubes.
So essentially you don't care about minus inverse beta. You just care about the local.
About minus what?
Minus inverse beta.
That's all the same, right? This is. I wanted to show that this is additive. This is the same. Okay, so we're going to try to define the energy for an isolated system in a box. And let me assume for simplicity that the background now is just 1. Okay, so now I have a box. I've zoomed, right? So I'm going to take boxes of size R. And I'm going to have a certain number of points here, which typical distances between the points are like 1. And I have my background, which is -1 in this box. And we're going to do it in 2 different ways. And see that it's interesting to have 2 quantities. So quantity 1 of my box, blah, blah, blah. And what I do is I solve in the box minus Laplace U equals the sum. So I have some little n points, right, of my Dirac's -1. And on the boundary, I have to prescribe some boundary data, basically, if I want to have a system in the box. So on the boundary, I'm going to take 0 Neumann condition. This is the boundary of the cube of size R, and this is the cube of size R. So this is like this. Right? Yes? And of course, the energy that I want to take for this one is I want to define energy. So I don't remember. I think I still call it F. No, it's this -1. It's not inside the sum. Right? This is the neutralizing background. So that's why I tried to put parentheses. It's this sum and then -1. That's the background. So we're going to define F of the configuration Xn in this box Q as this energy in QR. So that's one way to define energy. So you see a problem with this way? Yes, no?
Is there any condition?
A condition on what?
On the
Small n. Yes, there should be a condition on small n. That's the point, yes. So what do I need on small n? So you can solve this equation if and only if this whole thing integrates to 0, right? Otherwise, you cannot solve. So what is this condition? It's a neutrality condition, right? So if neutrality, in other words, n has to be equal to the volume of the box. Right? So your box has to be quantized, in fact, because you took this here we took this background to be 1. So for a quantized area box or volume box, I can solve this problem. If I have a neutral system, I can solve this, and I can define the energy like that. Sorry that things are a bit cramped, but I wanted to keep them on the same board. So this one's okay. The second one, I'm going to solve the same equation. And on the boundary, I'm going to put 0 boundary condition. So that's Dirichlet boundary condition. And this one you can always solve. That's OK. And then you can define an energy. So it's going to be called G. Of course, all these things should be renormalized, but now I told you that we're going to ignore that. And now we can define it. OK. So in principle, these things have nothing to do with our original problem, or no, they have something to do. Because you can think that if your box is becoming really, really large, the boundary conditions at infinity, they're not going to matter very much. Right? So if you let R go to infinity, somehow these two things should look like the original energy. And so the idea is to try to quantify how much they differ from each other. Right? So it's like you have a system in a very large box, so think R very large. You impose some different boundary conditions, but sort of in the middle, things should be a little bit insensitive to what's happening at the boundary. And so the total energy in the box, which we've learned scales like the volume of the box, should not depend so much on the boundary conditions. And the question is to quantify that. So the thing you can observe is that F is subadditive with respect to the boxes, while G is superadditive. What I mean by that is that if you have F of, let's say you take two configurations, and you put them in a union of two boxes, and two adjacent boxes, like this. Right? This is QR1, or whatever, QR1, QR2, more like that. I want to say that this thing is less than that. While the other one is the opposite. Okay, so superadditivity, subadditivity. These two things are true, and moreover, basically F is always bigger than G. So all these things are true and can be proven with a little bit of elementary elliptic PDE. Because after all, we can take advantage of the fact that we're dealing with Laplace's equation. So it's a very nice elliptic PDE. Laure, you're the chair.
Yes, more than 5 minutes.
5 minutes? OK, thank you. Okay, so I will tell you a bit about that to finish. So first of all, why is it that F is bigger than G? So one has Neumann boundary condition, one has Dirichlet boundary condition. So this is a simple fact from calculus of variations, that if you take if you take something like this, right, and you try to minimize, I don't know, let's call it integral gradient f squared in the cube among all functions such that minus Laplacian f is equal to some given w. Right, so you give yourself the Laplacian, you minimize the Dirichlet energy. Well, you can do variations. If you want to check this, so you try f plus t f prime, and you say that d dt of the energy of that equals 0, something like that. And you have to have f prime that respects the Laplacian condition, so it has to be harmonic. So you try it, you look at the conditions you obtain, and you'll obtain that f has to be constant on the boundary. So the minimizer has to be constant on the boundary. It's really not very difficult to derive. And so if it's constant on the boundary, you may as well assume the constant is 0, because you see this problem is invariant under addition of a constant. Okay, so the one that has 0 boundary condition is actually the one that minimizes the energy among all the things that have the same right-hand side. Okay, so if you can solve this, this guy in particular is a competitor, so it has to have more energy than this one. So this f is bigger than g. The super additivity then follows by the same reasoning, because if you have the union of two cubes, right, the thing is minimizing with respect to the big cube for all given right-hand side. So if you restrict to the left-hand side cube, it's a competitor, so it has to have more energy than the problem for the left-hand side cube with Dirichlet. And if you restrict to the right-hand side cube, it's the same. So this follows just by the same argument. Yes? And the subadditivity of f is a tiny bit more subtle, but not that much. The subadditivity of f is quite convenient. It follows from a little lemma that says basically that no, that's not the one I want to erase. This one. This one. Okay. I'm going to do it here. So if you have a vector field, with divergence equal to the Laplacian of a certain function h in a domain, and Neumann trace here is 0 on the boundary, and dh d nu also equals 0 on the boundary, then integral of grad h squared is less than the integral of e squared. And that can be proven by simply expanding e squared. So you say, okay, what is e? Well, e is grad h plus e minus grad h. Let's expand. So you're going to find it's bigger than grad h squared. There is a term E minus grad H squared. I throw it out because I just want an inequality. And I'm going to get 2 grad H dot E minus grad H. And now for this term, you integrate by parts or apply Green's formula. So you take the gradient, pass it on to that. It's going to give you a divergence. You can do it because the boundary conditions have a zero Neumann or a normal component 0. And the divergence of E is the divergence of gradient of H. So this thing is 0. Okay? So these are the assumptions, and so you have an inequality. So in other words, the gradient is the one that has the smallest Dirichlet, the gradient is the one that has the smallest Dirichlet energy among all vector fields with a given divergence. So it's basically saying that if you take a vector field, you can L2 project it onto gradients. You diminish the Dirichlet energy, provided that your boundary conditions are in agreement. Okay, so now you use this lemma. I'm going to show you how. And then we'll stop. To show the subadditivity of F. So if we have 2 pieces like this, and you have a U Q1 and a U Q2 in the cube, and then you also have a U Q1 union Q2 in the union, they each solve the Neumann problem that I deleted. So each of them solves with their Neumann boundary condition. Of course, the right-hand sides for the elliptic equations are always the same. So they have all the compatible divergences. So I'm going to define E equals grad U Q1 in cube 1 and grad U cube 2 in cube 2. This is a vector field. It's no longer a gradient, so you're just copy-pasting 2 different gradients. Doesn't make it a gradient. It's no longer a gradient, but it has the right divergence. So you can check that this is equal to that. Even though the vector field may jump here, the normal components are in agreement. So you have a vector field that jumps, but the normal component doesn't jump. And in particular, that doesn't create any divergence. So it is true that this is that. And so that becomes equal to the Laplacian of the thing on the union. And so now you can apply the lemma. So all the assumptions of the lemma you can check are satisfied. Is less than the integral of E squared. And that's equal to so that's the subadditivity. Okay, so tomorrow, Friday, I will wrap up the thing with that, explain to you that we can use these 2 sub and superadditive quantities to basically sandwich the true free energy and obtain the almost additivity and the local laws. So the idea is we're going to try to prove that there's one that's subadditive, one that's superadditive. So when you make the box larger and larger, one's going to be decaying per unit volume, the other one's going to be increasing. And we're going to be able to get an estimate on the difference between the 2 and show that it's small. And I will finish that on Friday. I will then switch to slightly different topic about fluctuations, so getting more information about the central limit theorems for fluctuations of linear statistics. And I also owe you another thing which I need to explain for a brief moment, how you can extend these methods to the non-Coulomb case, because now here I really used Coulomb in a very crucial way. So in Riesz cases, you can sort of use similar ideas, and I'll discuss that on Friday. Thanks for your patience.